I like to teach templates or just methods that you can throw over questions, and these will always work. So I'm going to talk about a template for finding the nth root of a complex number. So we've got w to the n is equal to z. Now w and z are both complex. So this is a complex number, this is a complex number. First thing we need to understand is that there will be n distinct roots. So you're going to get n answers if w to the n equals z. So your first step is to express this right-hand side. So express z. This is the first part of your template. Express z in terms of r, or mod z, e to the I outside of theta plus 2k pi. So the modulus of z is simply the r value. Theta, 2k pi, theta plus 2k pi, these angles are all what they call coterminals, so they differ by 2 pi. And we'll need to do that to pick up the multiple roots. When I do an example a little bit later on, it'll become a bit more apparent as to why I'm doing that. So we've got w to the n. Now just to express z as another way, as being mod z e to the I sine theta plus 2k pi, k being a constant integer, sorry, an integer. K will be an integer. We then take the nth root of both sides. We take the nth root of that, we get w equals, we'll just write the right hand side, e to the I theta plus 2k pi, we'll raise the power of 1 on n. Taking the nth root is like to the power of 1 on n. This can be split up as z to the power of 1 on n. A power raised to another power, we multiply, so we multiply this power times 1 on n, we get I outside of theta plus 2k pi all over n. So then our next step is to sub in values of k. And we use 0, 1, 2, all the way up to n minus 1. So, as I said, k has integer values, and we sub in values of k from 0 all the way up to 1 less than the value of n. And that will generate, if you go from 0 to n minus 1, that'll generate your n distinct roots. Alright, so that's the simple template. It's a way that if you work through that on all the problems you get, the numbers will change, but it's the same process that you're going to use. So let's just look at an example, and hopefully that'll make a little bit more sense. So find all sixth roots of 1. Okay, so we've got w to the 6th equals 1. Now 1 can be expressed as a complex number, and if we think of the number 1, forget about the fact we've got w to the 6th here, we'll just look at 1, and how can we express that as x plus iy, or r e to the I theta. So Archean diagram. We've got the number 1 as 1 plus 0i. So 1 plus 0i is just out there. So our mod z So we've got Z is equal to 1. That is 1 unit long. So mod Z is equal to 1. And the angle that makes with the positive real axis is equal to 0. So theta equals 0. So therefore, if we go back to our first one, express Z in terms of mod Z e to the I theta plus 2k pi. Mod Z is equal to 1 and theta is equal to 0. So we can substitute in there. So we've got Z is equal to 1 e to the I outside of theta is equal to 0 plus 2k pi. Okay, so that's step 1 done. So now step 2 is w to the n is equal to 1 e to the I sort of 0 plus 2k pi. Step 3 is to take the nth root, that's w to the 6, is to take the sixth root of both sides. So if we take the 6th root of w to the 6th, we get w is equal to 1 to the power of 1/6 e. Now instead of 0 plus that, we can just say that's I to the power of 2k pi, all raised to the power of 1/6, and that's equal to 1 raised to the power of 1/6 is just simply 1, so we won't write a 1 there. E to the I, now it'll be 2k pi, we're going to multiply these two indexes together, so it'll be 2k pi over 6, 2 over 6 is 3, so it'll be k pi on 3. Okay, so we've done this step up here, step 3. So our next step is to sub in values of k from 0 to n minus 1. Now n is 6, so we're going to do all the values from 0 up into n minus 1, 6 minus 1, 5. So k equals 0 will give us our first root, which we will call w0. We're going to have 6 of them, so we'll have w0 to w5. And we're going to put k equals 0 there. So that's I 0. So that's e to the I 0. I times 0, anything is 1. So anything raised to the power of 0, e to the power of 0 is equal to 1. So we step our k values up by 1 each time. So there's 1, so this will be called W1. There's E. Now up here, we're going to put k equals 1, so that'll be e to the I pi on 3. And then we do k equals 2, and that'll generate W2. Put a 2 in there, e to the I 2 pi on 3. K equals 3. So we're stepping up k by 1. So another one. Gives us W3 is equal to E. Now k is going to be 3, so that'll be equal to 3 over 3 will just be equal to 1, so that's I pi. K equals 4, W4 equals E to the I 4 pi on 3, and K equals 5, W5 equals E to the I, now 5 will be 5 pi on 3. So each of these has a modulus, a length of 1, and if you like we can plot them on the Argand diagram. So here's my real, here's my imaginary, All of them have a modulus of 1. The R value for each of these is equal to 1. So this is just equal to e to the I theta, so theta is equal to 0, we'll go out to there. The next one is also of length 1. This one's got length 1, this one's got length 1. So they're all going to appear on a circle of radius 1. They're going to be on that circle somewhere. And you can see there, this has got a modulus of 0, theta of 0, pi on 3, 2 pi on 3. So they're increasing the distance or the angle between each of these roots is going to be pi on 3. So if we go up pi on 3, so we've got W0 is out here, W1, and that'll be pi on 3. This is W2, this is pi on 3, because if you add pi on 3 plus another pi on 3, you get 2 pi on 3, which is W2 here. W3 is e to the I pi, so the argument is pi, so that's pi, so that'll be out here, W3. So there's another pi on 3, etc., etc. So W4, W5. Okay, so each of these will differ by pi on 3. All those angles in between will be pi on 3. So that gives you the 6 roots of w to the 6 equals 1. And if you look at it intuitively, you can see that, well, okay, 1 has to be one of the roots because 1 to the power of 6 is equal to 1. So that's that one over there. But equally so, you can actually see that each of these will also work. What happens if you don't stop at 5? If you keep on going, put k equals 6 in there, there was k equals 5, which generates that one. K equals 6 will actually come down and generate that one again, and then you just keep on generating the ones over the top again, which are no different. So that generates the 6 roots. There's the Argand diagram, and that's the sixth roots of 1.